Just realized I've been doing all my notes in the wrong notebook. Whatever. Anyway, 6-2 today, people. 6-2. 6-2 is all about sets, specifically subsets, where we talk a lot about. So here's a few definitions. Just want to walk you through them here so you can explain them to you a little better. This means A intersect B. So the idea of this is this. If you think about A and B are two sets, like in a Venn diagram, this where they overlap each other is A intersect B. Right there, that part right there. So there's a formula or a rule that says this: A intersect B is a subset of A, and A intersect B is a subset of B. Well, duh. In other words, this little piece here is in both circles. Nice. Okay. Also, check this out. So if A is a subset of A union B, and B is a subset of A union B. Well, let's see what that looks like. Here's A. Cool. Here's B. You know, I could do it like this, and we call these disjoint sets, like this, in a, if we were discussing probability, we'd say they're mutually exclusive, but they're disjoint sets. So A union B would be this guy and this guy. It would be all of it. So clearly A is a part of, if you count that A and B together as one whole set, obviously A is part of it and B is part of it. That's also true if they're not disjoint. So here they're overlapping. So A union B is this whole thing, and clearly A is part of that and B is also part of that. Okay. And then of course you'll recognize this guy. So A is a subset of B, and B is a subset of C. Then, wait for it, A is a subset of C. Oops, not of itself, you moron. Of C. Nice. What is this? Transitive property, baby. Transitive property. It holds, as usual. One shouldn't be surprised by this. Okay. Cool. So we're also then going to talk about this. So if you have a universal set means here's everything. Okay, everything is out there. Okay, so then X is a subset of the universal set, that is out of everything, and Y is also a subset of that. Okay, now it just kind of freaks everybody out. They're like, what does that mean? Like numbers? Sure. Kinds of cows? Okay. Brands of cars? Yeah, that's cool. Everything is counted in the universal set. So X might be, I don't know, dog names, and this might be birthdays of famous politicians. It makes no difference, okay, because literally everything is in the universal set. Okay, so check this out. So X, little x, is an element of X union Y. Okay, which implies this. Okay, this is an if and only if statement. X is an element of X, or X is an element of Y. In other words, the only way that little x, this is a little x here, the little x is in big X union Y. Now remember, big X union Y. This is big X. This is big Y. Little x is either going to be here, or it's going to be here, or it's going to be here. But in either one of those places, it's either in X or it's in Y. It wouldn't even matter if they were disjoint, because this is right now, that whole thing is X union Y. If X is here, it's in the union and it's clearly in Y. Okay? So X is an element of the intersection. This means if and only if X is an element of X and X is an element of Y. In other words, it's in the overlap between those two circles. Okay? So this is pretty exciting. Little x is an element of big X minus Y. These are also big X's and Y's. I'm sorry. Big Y, big X. All right, cool. If and only if, listen, X is an element of X and X is not an element of Y. Because if it was, there's it in both of them, and when you subtract, what would happen? It would go away. Okay. X is an element of X complement if and only if X is not an element of X. What do I mean complement? That means it's not X. Okay. Here is a very cool Venn diagram. Here's X, big X. Everything that's not in big X is in not X. So if little x is here, where is he not? He's not in X. But Mr. Groom, he's inside of Y. That's cool. Guess where he's not? He's still not in X. So X complement means everywhere besides X. Okay? And so X and Y as a ordered pair is an element of X cross Y if and only if X is an element of X and Y is an element of big Y. It's the only way you can match those up. In other words, you're going to take a value from big X and you're going to call it little x, and you're going to take a value from big Y and you're going to call it little y, and you're going to match them up this way. Well, you can't do that if this is not in here and this is not in here. Okay? So for instance, 2, 3, 7, that's X, and here's your Y, 1, 2, 1, or 1, 2, 4 rather, sorry. You cannot get 3, 7. Why? Because 7 is not in Y. You can't do it. Okay? Couple more, definitely, well, not couple more. There's quite a few more properties. We're going to run through them just so that you feel comfortable with it. So for unions, so A union B is obviously the same as B union A. You're just simply taking both sets and crunching them together. Okay? That's also true for the intersection. A and B is the same as B and A. Okay? That's where those two circles overlap. Doesn't matter which one you put which direction. Okay? Hey, so remember, this is, what is that property? That's the commutative property. Okay? So what other properties do we have? Well, we had the associative property back in the day, you'll recall, right? Associative. And so if you look at associative, it's right there. It's A union B union C is the same, of course, as A union B union C. Okay? Which is, yeah, I already got that down. And then the same thing is true for the intersections, of course. Like so. Okay? Nothing too exciting there. Ooh, say, that's key. What would the distributive property look like? Distributive, that means multiply. Not so fast, Haas. It could be multiply, but it could also be this. Is equal to A union B intersect A union C. Okay. And so think about that. It's pretty cool. It's pretty easy to do. Let's look at a picture of that one just for fun, shall we? If you got A here, you got B. Well, actually, let's do this. Let's don't do it with circles. That's too hard. Let's do it this way. Let's do, so A is 1, 2, 5. C, yeah, B, well, I don't care. B is 2, 4, 5. And C is 1, 3, 5. Okay? So look at this here. I want to do B intersect C. Well, they intersect at 5, yes? Boom. That's where this is B intersect C. Nice. And now I want to take A and I want to union it with this. And so I'm going to get the 1 and the 2, obviously, from A. And then, of course, I already got a 5. So this is the union of that. So it's A union of B intersect C. Okay? Now, what this says, I could take A union B first, and so that would be 1, 2, 4, 5. And I could take A union C, so that'd be 1, 2, 3, 5. And then I ask you again, where do these guys overlap each other? 1, 2, 5, which is the exact same answer. Okay. Could you do it the other way around, Jay? Could you do a union B intersect C and a union B? Wait, did I just do that one? Is that the one I just did? No, I did it right. No, damn it, I did it wrong. That's the one I did last time. There we go. Cool. So that'd be A intersect B union A intersect C. Again, if that was the same thing up here, where did A and B intersect? They intersected the 2 and the 5. Where does A and C intersect? The 1 and the 5. Where do these guys intersect? So 1, 2, and 5. That would be their union of those sets. Okay? Pretty straightforward. So if you take A and you take the union of A with the empty set, by the way, your book uses this for empty set. I prefer this for empty set if you're asking me. It's just A, okay? Because you're not adding anything to A. And what has happened, you take A and intersect it with the empty set. What do they have in common? They got nada in common, senor. Nada. Okay? So you can do that. So you can do that way. And then, of course, they give you this one as well. What does A intersect? The universal set. So this is dog names. This is literally everything that could possibly be. Where do they intersect? Dog names. Okay, that's what they have in common. Clearly, if you take A and you union it with not A, right, or A complement, what do you get? We literally get everything. So you get the universal set. Okay. If you take A intersect not A, what do you get? Well, I got nothing in common, so the empty set is what you get, my friend. Okay. If you take the complement of the complement, what are you going to get? What's the complement of A complement? It's just A. Boom, done. A lot of these are pretty straightforward. The idempotent laws. So A union itself is, well, itself. Okay. A intersect itself is A. Cool. You don't need the. You try to impress people by calling and quoting it as the idempotent rule. I don't think anybody's gonna be that impressed with you, but you go for that. I think we took care of that one already. Got that one. Ooh, that's a fun one. Here, let's try this one here. This will be fun. And no, I will not hold you to these guys' names. This is De Morgan's law. Cool. Weird. Interesting. Let's see what happens here. So here's A. Well, actually, I want to do A that way. Let's do A. It's 1, 2, 7. B is 2, 3, 7, 8, whatever. Q. Oh, actually, I don't want to do that. No, I don't want to do that. No, I don't want to do that. Let's do A this way. Here's A. And here's B. Nice. Nice. Here we go. Cool. Okay. Right. Cool. All right. Interesting. So this is A union B. That means everything on the outside of this is the complement of that. Well, that's nice. So what is A complement? A complement, I'm going to get a different color pen here. A complement is this green stuff. This is A complement. Are you with me? Now, what is B complement? Well, B complement is this junk out here. Okay, well, where do they intersect one another? Well, they intersect one another where? Where A is not, and, well, so they intersect everywhere where A is not and B is not. Okay, so you can see that's where they overlap one another out here. The B and the A, you can see, are not shaded at all. I mean, they're shaded. They're shaded, I should say, but they're only shaded once, not twice. It's everywhere the double shading shows up. That's what we're talking about. Okay. And then, of course, A intersect B complement is equal to A complement union B complement. Okay, think about that for a minute. So here's A, here's B, cool, whatever. So this is A intersect B, right there, right? So where's the complement? It's literally everything else but that, okay? So what are you going to have? Well, you're going to have they're basically the same picture, except notice how this inside piece is not shaded right now. Do you see it? It's literally everything on the outside of that piece right there. That is what we're looking for. And so it's everywhere that it's at least one time shaded. That's what we're saying. So if you were to draw this picture, not A would be everything including B shaded in. And not B would be everything including A shaded in, except for this little, and the only place where where you wouldn't be shading is in that little divide right there. Okay. And so there it is. The only place where there wouldn't be any shading at all. What do we got here? So the absorption loss. Oh, okay, cool. You don't. Again, I will not hold you responsible to this piece. With the names, rather, anyways. But I want you to feel good about them. A union A. Okay. And did I get that right? No. Sorry, lied to you. Not there. I was on the wrong one. Cool. See, listen. Where does A intersect B? What does that give us? I don't know. Let's find out. Let's do this with some numbers, just for fun. So A intersect B would be 2 and 7. If you take A, which is 1, 2, 3, and 7, you get the union of that. What do you get? Well, you get 1, 2, 3, and 7, which is what? It's simply A. Okay. Could do the same thing with A intersect A union B. Okay. So A union B would simply be 1, 2, 3, 6, 7. And then I have 1, 2, 3, and 7. And I want to know where they intersect one another. 1, 2, 3, and 7. It's A again. Okay. Call it the absorption rules because basically you absorb the B. That's the idea of it. It's pretty straightforward. The opposite of the complement of the universal set is the null set, obviously. It's the opposite of everything is nothing. The opposite of nothing is everything. So they're complements of one another, obviously. And if you do A minus B, you will always get A intersect B complement. Okay. So in other words, it's pretty straightforward. I like to look at this one as the actual problem. So you have 27 minus 17. Well, you're going to get 10, right? Okay. What did you subtract? Well, you subtracted what was not in B, is the idea of it there. Okay, you can think of it that way. So it's you have A and where that intersects with what's not in B. Okay, so what's A with what's not in B is there's 10 left over. Maybe that's not as good for you. Maybe you want to look at it this way. 1, 7, 9, 12, 15. If this is A, and let's say B is 7 and 9. Cool. Then what are you left with? Well, you're going to take A intersect with B complement. All right. Well, B complement in this case. B complement is everything that's not 7 and 9. Yes? Okay. So it's everything that's not 7 and 9. So what is in this set of data here that's not 7 and 9? It's 1, 2, 1, 12, and 15. That's how that works. Okay. Yeah, nice. A few more, I think, of these little dudes, and we'll go do a few examples. I think it's helpful to see them kind of spelled out because sometimes it doesn't make a lot of sense, I don't think. Cool. So if you're going to prove, so they do some proofs in this chapter, so we'll kind of work through a few of them. So on page 356, they talk about how you could prove that two sets are equal. You'd have to show, well, another way of saying that is to say that they're both subsets of one another. That's how you would show that they're the same. And then they do some proofs for the distributive law, okay, and proofs for these other laws. I didn't prove them. I demonstrated how they work, okay? I didn't set out to prove them, and you can look through the proofs on your own, and see if you like them or not. Okay, for the most part, the uniqueness of the empty set, there's only one of them, clearly. the empty set is a subset of everybody. Okay. The element. So all those are pretty straightforward things here. Okay. So what we're going to do is we're going to look through a couple of them here and kind of work our way through them. I gave you a few examples from this section to do a little proofs on. They're not bad, I don't think, but they're not terrible or fun either, I don't think necessarily. So the following is a proof. It's already set up for you, kind of, for all sets A and B. If A is a subset of B, then A union B is a subset of B. Where did I go? Yeah, fill in the blanks. All right, cool, nice, nice. And so there it is. Awesome. So if A is a subset of B, then what do you get when you do this problem? Let's kind of talk ourselves through here. Well, if A is a subset of B, then that means that what happens? That means that if I were to draw this picture, here's B, here's A. That's what we're saying. So then what would these two have in common? Everything that B has. Okay? That's how the thing's going to go. So it tells us the following. So it says, suppose A and B are sets, we must show that, so in parentheses, we must show that what is true. Okay? Well, we must show that, so anyway, so we want, just a second. Okay, so as I say, they give us the head start on this. So it says, so we're going to suppose A and B are any sets. This is what they give us. Any sets. And A is a subset of B. Cool. Okay. So we must show that blank. Okay. We must show blank. Okay. So then what do we have to show here? Well, for this to be true, we need to show that this is true, right? That's just what they want us to repeat this. They'll regurgitate that bit right there. Okay, great. Then it says this. It says, so again, this is part of the problems that they have worked out for us to this point. So we're going to let X be an element of what? Okay, we must show, so we're going to say let X be an element of blank. We must show that blank. Okay, so who does the X have to be an element of? Well, let's think about this right now. So what do we have? Okay, so X must be an element of who? Now let's think about that for a minute. So X must be an element of A, okay, but we must show that X must be an element of B as well, right? An element of B as well. That's what we have to show. Because what we need to do is when we do the union of those two sets, okay, we really just need to have it to where it's inside of B. It needs to be fully contained in B. Okay, so that's cool. Now, interestingly enough, this is a true statement. So back on page 361, there is this little theorem right here. It says that for any sets A and B, if A is a subset of B, then A intersect B is equal to A, and wait for it, A union B is equal to B. Okay. And so we can walk through that right there. So there it is right there. And so if you're looking, the one we're actually working on, in essence, is what they showed us on that page right there. Okay? So we must show that X is an element of A intersect B. Okay? So, okay, yeah, so actually we must need to show that X is in the element of A intersect B. That's what we need to show. Okay? So that's on page 361 there. Now, I am not the best at proofs, so I wish I wasn't the one teaching you this part of it, but that's how life goes. So in case X is an element of this, since X is an element there, then it will be in there. Okay? So it says in case, by definition of the union, of union. Okay. By definition of the union, X is an element of blank blank. X is an element blank. Okay. So let's go actually look that up, shall we? So the definition of a union is back on page. Okay, so it just says symbolically X, A union B, X is contained in, X is an element of U, such that X is either in A or is an element of A or an element of B. Okay, so X is A or B. Okay, like that. Okay, that's what it means to be in the union. That's by definition of the union. Okay. So X is an element of blank. So again, that's back on page. Darn it, I lost my page here. And if you keep going here, it says, in case X is an element of A, this is part G, if X is an element of A, then because A is in B, it works. And obviously if X, and then the next part, if X is, in case X is an element of B, then clearly there it is. So in either case, X is an element of B, as was to be shown. Okay, I'm sorry, X is an element of, X is an element of B, as was to be shown. That's kind of a muddled proof. I am not going to get too hung up on them. Pretty much just kind of walk through them. I'll try to do another example later in a different video for you, probably. I'll see if I can do one that's a little more clear. Maybe I'll try another one right now. We'll see. Let me pause for a sec. Okay, so on this one, for all sets A and B, we need to prove that this is true. Okay, so think about that for a second. Okay. Okay, so first things first. Okay, for that to be true, we need to look at X. We need to have him be. We need to show that X is an element of, or we got to figure out where X is. I should put it that way. So let's find out where X is. So if X is an element of A, all right, then where's that going to put it? Well, clearly that'll be in the answer regardless, because where I take this guy and this guy, whether I intersect them or not, I'm going to union this with whatever's in here. So if X is in A, then clearly it's in my final answer. So that works. And if you discuss that through me like that within words, so if X is an element of A, then by definition of union, it is in A union A intersect B, therefore equals A. Okay, we know that. And so then if our X's were in there, we're good to go. If X were in B, or an element of B, well, we need to think about this. Well, remember, we got to think to ourselves, basically we're proving the distributive property is what we're saying here, right? Except what we're saying is that we're proving the distributive property. Remember, this is the absorption principle, So that's what we're proving here in this guy. So if X was in B, that's cool. Then even if A and B have nothing in common, the intersection piece here, right, what ends up happening is that even if this part here were then A intersect B would be the null set, correct? Right, if we're talking about that one only thing, right? So if X was only in B but not in A, and that's the only part we were interested in, then A intersect B would be the empty set. But then what would A union the empty set give you? It would give you A, and that's one of the definitions back in the page over there. If you write this down for me like that, therefore, and then you give me one of these whole therefore, regardless of where it is, regardless if in A or B, it will be in the solution. Okay, if you spell it out like that for me, I'm pretty okay with that. I do not need to see a lot of this action. I don't need to see a lot of, such that's and this and that and the other thing. That's cool if you're into that. I'm more along the lines of can you prove it. But again, what needs to happen is this. by this absorption principle, X can be one of two places. And when we say X, whatever X is, it could be in here. If it's in here, which means it's also in here, then it doesn't matter what goes on in here. It's out here. This union anybody, it'll still be in the final answer. Sweet. If it's in B, then it doesn't matter if there's an intersection or not. The intersection could be the null. It could be. It could be anything. Okay? And not A. Okay, then obviously the intersection is the null set, and then A union the null set is A. Cool. And of course, if it's in A and B both, well, then you're good to go, right? Because really, we're only interested in if it's in A or B. If it's in both, well, you're clearly fine. Okay? This is the kind of thought process I want you to use when you think them through. I don't want you to spend an hour, like 25 hours doing them. Just kind of think them through quickly, and let's get going on this thing. Okay? So let's do one more, I guess, and then we'll call it a night. For all sets A, B, and C, let's get A, B, and C. If A is a subset of B, where am I at? Then A union C is a subset of B union C. Cool. All right. Awesome. Okay, now think what that means for a minute. Okay? So, if X is an element of A, right? And then of course X is an element of B. That is the definition of subset, right? Because A is a subset of B. So if it's in A, it's clearly in B as well. Sweet. Awesome. Okay. Now, what do I know about this? So, well, what are we going to say here? So, then if you take therefore, I could probably just give one of these. You can give me a therefore. You can say therefore that X is an element of A union C by the definition of union. X is also in B union C, clearly by definition of union. That's true. Okay, beautiful. Those are true statements. Now, does that mean that this guy is inside of this guy? Does that mean that? Now I haven't proved that yet. I don't know if I'm going to want the therefore yet. But because of this statement here, then this stuff here is also true. Okay, so we know X is in both of them. But I want to know that it's fully contained. One moment while I think about that. Just had my magic pin down somewhere, and then I couldn't find it for a second. Sorry. Now, think about this. So by definition, okay, that this is true. Okay, if X is an element of B. Okay, and of course it's in there. Great. But we have to make sure that we're good here. Okay, so let's think about this for a minute. Let me back this train up a little bit. So if X is in A, okay, then clearly it's in B, therefore it's in the union. Piece of cake, no problem, okay? However, okay, remember what we're actually saying here is this. If X could also be in an element of just C, are you with me? X could be in an element of C. Ugh. Okay, what does that mean then? Well, then it is also an element of an A union C, obviously, and B union C as well. Obviously, that's true as well. Okay, but that's great. So then, if it's in C, it's in both of them clearly, and if it's in A, then it's obviously in B. The idea being is that this piece here, the C pieces, all right, are bigger pieces, but they're common to both sides. In fact, if we looked at it, it looks very similar to algebra. Whatever you do to one side, you must do to the other side. So if it's true that my X is actually in C, then by putting the union with C on both sides, clearly this is the bigger one. This obviously subsides inside of this guy because this is a piece of this guy. So therefore it has to be inside of both of them. If X was in A, then clearly it's a subset. And so then all you have to do is show then it could also have been in C. Okay, there you go. So in either case, it's this case or this case. In either case, it works that they're a subset. I will let you be somewhat. I am not. This is not a. You are not a math major. Good Lord help me. I don't know how I ever became a math major, but fortunately, I only had two horrible classes when it was all proofs. And I got decent at them then, but I'll tell you what, they were algebraic proofs. They weren't a lot of this set proofs. So algebraic proofs I'm a lot better at, thankfully, and some calculus proofs. I'm a lot better at those guys than I am at this. I'm not great at those either, but I'm better at them. Okay, so for this section, all I'm going to ask you to do is there's just a couple of homework problems, and you're going to work through some of the proofs. And when I say work through them, I mean talk your way through them is what I'm going to be asking you for. There probably will not be, if there is one on the test, and I don't think there will be, I think it'll be on a quiz. I think it'll be just on a quiz. It'll just be walk me through it step by step how you did it as best you can. Okay, that's kind of how it's going to go. It won't be on the test because there won't be enough time.